You ever find yourself just shivering through one of those brutal cold snaps? You glance at the news and you think, wait a second, isn't the planet supposed to be warming? I mean, it's a question a lot of us have asked. It feels completely backwards, right? Well, it turns out there's this fascinating and pretty intense scientific debate happening right now about this very paradox.
All right, so let's just dive right into it. This is the big mystery we're going to try to unravel here. Is there a real physical link between a rapidly heating Arctic and the kind of crazy winter weather that can just paralyze entire continents, or is it all just a coincidence? So here it is. This is the core of the puzzle, laid out side by side. On the left, you've got the Arctic, and it has been warming at an absolutely blistering pace. We're talking more than double the global average. But then look at the right. These are the winter temperatures where most of us live, in North America and Eurasia. They've basically flatlined, almost no warming at all. And in some recent stretches, they've actually gotten colder. This pattern, what scientists call warm Arctic, cold continents, this is the #1 clue in our investigation. To even begin to understand what might be happening to our weather, we have to look north first. We have to go to the epicenter of all this change. We need to talk about a phenomenon that scientists have a name for: Arctic amplification. So what is Arctic amplification? Well, it's pretty much exactly what it sounds like. The warming that's happening from climate change isn't being spread out evenly across the planet like butter on toast. No, instead it's being amplified, or kind of supercharged, right at the top of the world. And that's the reason the Arctic is just heating up so much faster than anywhere else. And this isn't just one thing, It's this incredibly powerful feedback loop. You can kind of see the cycle here. As the bright reflective sea ice melts, it exposes the dark ocean water underneath, which then absorbs a lot more sunlight. Well, that warms the ocean, which, you guessed it, melts even more ice. Then you add warmer air moving up from the south, and it acts like a blanket trapping that heat. It's really the perfect storm for putting warming into overdrive at the pole. Okay, so the Arctic is overheating. How does that end up affecting us way down south? Well, a really big group of scientists thinks this warming isn't just staying up north. They argue that it's actively messing with one of the biggest drivers of our weather, the polar jet stream. This quote right here from the National Snow and Ice Data Center, it really gets to the heart of the whole idea. See, the jet stream is basically this fast-moving river of air way up high in the atmosphere. And what gives it its speed, its strength, is the huge temperature difference between the freezing Arctic and the warmer areas to the south. So what do you think happens when you start shrinking that temperature difference? This is the proposed chain reaction. Step 1, the Arctic warms up so that temperature gap between north and south shrinks. Step 2, this puts the brakes on the jet stream, weakening it. Step 3, a weaker jet stream doesn't flow in a nice straight line. It gets slow and lazy and wavy, with these big meandering loops. And here's the absolute crucial part. Step 4. Those huge southward dips in the wave can literally grab a chunk of the polar vortex and drag it way down south, delivering those insane cold snaps to places like Texas or deep into Europe. Now, the evidence for this whole theory comes from just looking at what's actually been happening in the real world. Observational studies keep finding this really strong correlation. When the Arctic is unusually warm, the continents tend to get unusually cold. They also see more of these things called atmospheric blocking events. The best way to think about it is like a giant boulder suddenly appearing in that river of air, forcing the weather pattern to get stuck in one place for days on end. And that can lead to a prolonged heat wave, or, in our case, a very deep freeze. But, like any good scientific debate, there is another side to the story. A whole other group of scientists looks at this exact same data, and they come to a totally different conclusion. They argue that what we're seeing might just be the climate's natural, random, chaotic behavior. And here is the absolute crucial point for their counterargument. When scientists run these incredibly sophisticated computer simulations of our climate, the very models we use to project what the future will look like, they almost never reproduce this effect. In the virtual world of these models, melting the Arctic just doesn't consistently lead to a wavier jet stream or colder continents. So, from the modeling point of view, these crazy winters are probably just a roll of the climatic dice. It's internal, natural randomness that really has nothing to do with melting sea ice. Some of the research even suggests that warming in one part of the Arctic might create an effect that cancels out the effect from another part. So basically, they're arguing that this warm Arctic, cold continents pattern we've been seeing is a correlation, sure, but it's not causation. So what we have here are two camps. We've got the observation-based scientists who see a really clear pattern in the real world, and then we have the model-based scientists whose simulations just don't back it up. So why the huge disagreement? Well, it really comes down to this fundamental disconnect between what our eyes are telling us and what our best predictive tools are showing us. And this slide right here lets you see the problem for yourself. On the left, that's reality, the warming we've actually gone out and measured in the atmosphere. See how intense that is and how deep it goes right over the polar region? Okay, now look to the right. That's what the average climate model simulates. The warming is way shallower and the center of it is shifted south. The models, for whatever reason, just aren't fully capturing how intense the Arctic amplification really is. And this chart really shows the result of that disconnect. Get this. The models, on the left, predicted that our winters on the continents should have been warming at a pretty good clip, almost 0.4 degrees Celsius every decade. But the bar on the right, that's what we actually observed. In reality, it's zero, no warming at all. This massive gap, this divergence, is the absolute heart of the entire debate. It's this exact gap that makes it possible for two totally different scientific consensuses to exist at the same time. You've got one group saying, hey, trusty observations, something is clearly going on. And the other group says, look, the models are our best guide for cause and effect. And they say this is just natural variability. And it's entirely possible the models are just missing some key piece of the physics.
Now, this doesn't mean scientists are just stuck, yelling at each other. This whole debate is actually pushing the science forward. And researchers are starting to find some common ground, especially when they zoom in a little bit from the huge hemispheric picture.
So while the jury is definitely still out on that huge hemisphere-wide effect, there's a much stronger agreement on more local connections. For instance, a lot of studies now, from both the observation and the modeling camps, support the idea that losing sea ice in a very specific area, like the Barents and Kara Seas just north of Russia, has a direct downstream effect that contributes to colder winters over in Asia.
Okay, so after all that, what's the takeaway? Where does this really intense scientific mystery leave all of us as we try to think about what our winters are actually going to be like in the future? You know, ultimately, figuring this out is not just some academic exercise. It has massive, real-world consequences. Do our cities need to budget for milder winters with way less snow removal? Or do they need to be bracing for more frequent, more extreme, and way more costly cold snaps that can just cripple our infrastructure? Right now, the science points in two very different directions, and figuring out which of those paths is the right one, well, that's one of the most urgent and fascinating challenges in climate science today.